Is your machine learning model feeling a little too complicated? Sometimes, the simplest tools are the most effective. Logistic regression is the robust, interpretable model that every data scientist should have in their arsenal, and we are going to apply it practically using Python's scikit-learn. Forget the black box, we'll break down the code so you understand not just how to predict, but why the prediction was made. In this video, we will cover a brief explanation of what is logistic regression model, followed by a walkthrough of implementing it, reviewing the attributes, some hyperparameter tuning and multi-classification implementation. Logistic regression is a fundamental statistical model and machine learning algorithm mainly used for binary classification. Despite its name, it's used for classification, not regression. It works by modeling the probability that a given input belongs to the specified class. It first calculates a score using the intercept, coefficients and input features and computes a score. Then, it uses a logistic or sigmoid function to condense the score into a probabilistic value between 0 and 1. The probabilistic value is compared against a benchmark, which then determines the model's predicted label. The model also uses a log loss or binary cross-entropy model to measure the loss function. We will start coding in Python by importing the necessary libraries. We will load the first dataset we will be using from the scikit-learn library, which is the breast cancer Wisconsin dataset. It is a classic simple binary classification dataset. We will extract the dependent and target variables separately, and then print the description of the data along with the feature names. We can inspect the results to understand it better. If we scroll the output, we can see a brief overview of the dataset, with the number of records, features, and what the features mean. Further below, the minimum and maximum summary statistics of each feature is provided, along with any missing attributes, and the class distribution. As we can see, this dataset has been curated and is quite clean for usage. Next, we will load the data into a data frame for ease of reading data. We can print the head to inspect it. We can then prepare the data for training the model. We will not pre-process the data, as you will see later on. The model has a good accuracy score. We will split it and divide it between training and testing dataset. We will allocate 20% of the data for testing, and fix a random state so that we can replicate the same split for subsequent runs. Once that is done, we are ready to train the model. We will load the model with the default parameters and print the accuracy scores for both the training and test dataset. The accuracy scores for both seem to be quite good, hovering around 0.95. Below the score, there is a warning message that convergence failed to happen within the iterations. We can ignore it for now as the model is still trained successfully. Now that the model is trained successfully, we can use it to make predictions. Let's try to predict the first record of the dataset. We will print the actual result in the first row. We can see that the actual result is 0, which, since it is a binary classification, means that it is benign. In the next line, we can print out the model's prediction by using the model's predict function with the X features as inputs. The model predicted 0 correctly, which is a benign tumor. In the last line, we can print out the model's predicted probability of the class output. We do so by using the model's predict probability function with X features as inputs. This time, we see that the output is an array with two float values. They are the model's predicted probability of the two classes, 0 and 1, and benign and malignant respectively. The first value is very close to 1, which refers to the model's predicted probability that it is very certain that the instance is benign, while the second value, which is negligible, is just the difference between 1 and the first value, since all the probabilities of the outcomes must sum to 1. For the logistic regression model, the default threshold to decide if the model predicts it to be 0 or 1 is 0.5. It seems that the model has a very high accuracy score. But what if we want to improve it further by adjusting the model prediction score? How do we go about that? We will first start by looking at the model's prediction distribution before deciding on a suitable threshold to adjust. Let's load the test data into a new data frame. This time, we will include the actual results, the model's predicted results along with the corresponding predicted probabilities as well. We can plot a histogram plot of the predicted probabilities, with a hue of the predicted results. Blue bars represent 0, while orange bars represent 1. From the chart, we can see that the default threshold is indeed 0.5, with values below 0.5 being predicted as 0 while any above as 1. Next, we can plot another histogram plot of predicted probabilities, but this time, the hues will be the actual results instead. This time, we can see that there are some benign tumors, which were predicted incorrectly by the model, indicated by some blue blocks in the bars above 0.5, and some malignant tumors, which were also predicted incorrectly, as indicated by orange blocks in the bars below 0.5. Oh well, we can't get it all correct, but we can try. We can also print the description of the distribution to view it numerically. It seems that the data is skewed towards predicting malignant tumors, as evident by the histogram bar charts previously, and the fact that the predicted probability at the 25th percentile is 0.96, with a mean of 0.93. There doesn't seem to be a clear indication of which threshold is ideal. This will depend on the metric that you are trying to optimize. But for this case, let's say for argument's sake, that the impact of a false negative an actual malignant tumor, but the model predicts it to be benign, is worse than the impact of a false positive a benign tumor, but the model predicts it to be malignant. In this case, we will want to lower the threshold to allow the model to predict more to be malignant. The threshold is set arbitrarily to 0.4, but feel free to try different thresholds. We can then use this threshold and create a new list of predicted values with the new threshold using list comprehension, and use this list as the new predicted values. We can print the accuracy and precision scores to compare the variances in prediction based on different thresholds. Based on the results, as the threshold is lowered to 0.4, we can improve the model accuracy and precision score slightly. Apart from being able to predict the class probabilities, we can also predict the log probability using the model's predict log probability function. Why one might prefer to use log probability as a means of probability prediction is to handle small values, which the computer might compute incorrectly due to rounding to 0. Log probabilities represent these tiny numbers as large negative numbers, which are easier for computers to handle accurately. We can see how the probabilities are converted by referring to the last line, where the exponential of the log probabilities will give the same results as the original predicted probabilities. Now that we have gone through some of the useful model functions, let's move on to the model attributes. They are suffixed with an underscore at the end. We can see the number of features and the classes with the attributes n features in and classes respectively. Next, let's turn our attention to the intercept and coefficients of the logistic equation used by the logistic regression model. We can access them easily via the attributes intercept and coefficient respectively. These would be the beta values in the logistic regression equation. The coefficients are in order of the feature names. For example, the first feature is mean radius, and its corresponding coefficient would be 1.7. With the coefficients, we would be able to extract the feature importance from the model. We will extract the coefficients to a data frame and sort by absolute value of the coefficients. This would tell us the features of the model, which would explain the model's probability prediction. In the data frame, I have sorted the top 10 absolute coefficients of the model in descending order. From here, we can see that the feature worst radius has the highest coefficient at 1.74, and it will actually increase the probability of the model's prediction of the data instance being a malignant tumor. Conversely, for the feature worst concavity, the coefficient is -1.28, which means that it will actually decrease the probability of the model's prediction of the data instance being a malignant tumor. Next, we can use the logistic formula to derive the prediction value. We will use back the same prediction record we used previously, with the actual target value of 0. Then, we can print the model's prediction probability for comparison. Lastly, we can print out the result of the probability computed from the logistic formula. We will perform a matrix multiplication of the coefficients along with the instance feature values, add the intercept value, sum it and apply the logistic function accordingly. The result, as you can see, is the same as the model's predicted probability for malignant tumor. We can prove the mathematics of the prediction probability based on the logistic formula. What if we want to know what is the impact of a 1-unit change in the feature value? Let's find out. We will first assess the impact of it on a feature with a positive coefficient. Previously, we have found out the top positive important feature is the worst radius. Let's use that. We will copy a record instance and print the current worst radius value of it. Then we will print the current predicted probability for comparison. Next, we will increment the feature value by 1 and print the new predicted probability. We can see that immediately, the predicted probability increased quite a fair bit. The new predicted probability is 5.72 times the previous probability. We can repeat the same for a feature with negative coefficient, using the feature worst concavity. This time, we see that the predicted probability has decreased significantly. The impact is huge, for a 1-unit increment. The change in feature unit value doesn't have a linear change, but rather an exponential change instead, which is expected due to the nature of the logistic formula. For hyperparameter tuning, there are a few parameters we can tweak to improve the model results and performance. In the next section, we will go through solvers, penalty, tolerance and see. From the Scikit-learn online resource, there are a few solvers you can apply to the logistic regression model. Solver is the specific algorithm used to find the optimal weights or coefficients that minimize the cost function, and different solvers are better suited for different situations. For this dataset, we can test to see which solver has the best performance. Of course, there is a grid search CV module to do hyperparameter tuning, but for this case, we can just iterate through the solvers and print the accuracy scores. For this case, the scores are fairly close to each other. Referring to the online resource again, we can see that only liblinear and saga solvers have more than one type of penalty available. L2 is the default penalty for all the solvers. L2 adds the sum of the squared values of the weights to the cost function, penalizes large weights heavily, forcing the weights to be close to 0. This prevents any single feature from having too much influence and is a great general-purpose way to prevent overfitting. L1 on the other hand adds the sum of the absolute values of the weights to the cost function. It forces the weights of less important features to become exactly 0, creating a simpler, more interpretable model. The last available penalty, elastic net, is just a combination of L1 and L2. We can run the penalties with the applicable solvers and print the accuracy scores as well. There doesn't seem to have much improvement. Toll, or short form for tolerance, is a stopping criterion which tells the model's solver when to stop trying to find a better fit. Decreasing the value will make the model train for longer, and increasing the value will speed up the model training process. We can run a few tolerance values and view the results as well. The parameter C is just the inverse of regularization strength, where smaller values specify stronger regularization. Similarly, we can run a few values and see the results. You may have noticed that during the printed results, there are quite a number of warning notifications saying failure to converge. You can change the max iteration parameter to increase the number of iterations so that the solver can converge. The default setting is 100 times. Previously, the use case for the logistic regression model was on binary classification. But we can actually apply it to multiclass problems as well. This time, we will load the wine dataset. We can print out the entire set of predicted results. This time, we see that there are 3 possible target values. According to the Scikit-learn library, we can implement the logistic regression model directly using various solvers except liblinear, as they are able to minimize the full multinomial loss. For this case, let's try the Newton CG solver and print the accuracy, precision and the predicted results. We can see that it's working nicely. Apart from implementing the model directly from Scikit-learn, we can use another method called the one versus the rest classifier. Essentially, it breaks the problem down into building multiple binary classification models, comparing each target value against the rest. For the case of our wine dataset, it will build one model to compare the target value of 0 against the rest, and another model to compare the target value of 1 against the rest. Finally, it will build another model to compare the target value of 2 against the rest. For each record instance, it will run the 3 models and take the highest predicted probability of the models as a prediction output. We can test it out. We will fit the logistic regression with the liblinear solver into the 1 versus rest classifier and print the accuracy and prediction results. It works just as well. In conclusion, logistic regression isn't perfect, and that's okay. It won't handle nonlinearities that well. It can oversimplify, and it's not the most flexible model out there. But what it does give you is transparency, speed, and interpretability, 3 things every data scientist needs. Sometimes, the simplest tools teach you the most about how data actually behaves. And that's the end. Hopefully this has been helpful to you. For those who are interested, I will be sharing the link to my notebook in the description section of the video. Do you have any thoughts on it? Feel free to comment in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.